In this lesson, we are going to start our coverage with group 7 elements. And as we looked at some other elements of the periodic table, like group 4, we shall realize that we need to know the electronic structures or the configurations. We need to know the bonding and structure. We need to know the variation of physical properties of these elements, how they are prepared, how they react, and any other information that would be interested to know. But in this lesson specifically, it may take us long because I really want to cover all the physical properties of these elements. Then we can see what can follow. So for this case, I want us to cover the general chemistry, the introduction, and the physical properties. So in this case, let's begin with the electronic configurations of these elements. Before we go there, I want us to first know that if you talk about electronic structures or configurations, we are looking at the arrangement of the electrons of these elements, okay, in different sub-energy levels, okay? When we say group 7 elements, they can be known as halogens, or one can call them salt makers, but the common term that is known is the halogens. So to begin with the configurations, from the configurations, we end up getting the general outermost electronic configuration. Okay, so we are going to find that they have the same outermost configuration, and that is what we are going to find out here. So we shall have atomic number. Then by having the atomic number, you can easily write the configuration. Beginning with fluorine. Fluorine has got atomic number 9, and therefore its configuration will be 1s2, 2s2, 2p5. That is fluorine. Then when we look at chlorine, chlorine has got atomic number 17, implying that its configuration is 1s2, 2s2, 2p6, 3s2, 3p5. So that is the configuration of chlorine. Then bromine has got atomic number 35. And if we are to write its configuration, it will be 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p5. That is the configuration of bromine. Then iodine has gotten configuration, rather atomic number 53, implying that the configuration will be 1s2, 2s2, 2p6, 3s2, 3p6, all right, 3d10. From 3d10, we go to 4s2, 4p6, 4d10, 4d10, then 5s2, 5p5. So now looking at all this, you find that we end up with the s2p5, 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 s2p5. But before s and p, there comes different figures. For this one, there comes 2, 2, here comes 3, 3, here comes 4, 4, here comes 5, 5. Meaning that we can conclude by looking at these configurations, we can conclude that the outermost electronic configuration of group 7 elements is any s2, any p5. This is the outermost configuration of group 7 elements. They can ask you, they can say state the outermost electronic configuration of group 7 elements. So we have seen that from the configurations, they have it the same way. Now, after that, I am recording this. So in case one needs to review much, you can keep praying it over and over again. Then after that, we've got what we call the bonding and structure. Bonding and structure is the one that gives us some clue about the melting points, boiling points, right? So bonding and structure, we really need to know how the structures of these elements are. Now, fluorine as an atom, chlorine, then we've got what we call bromine, and finally iodine are all covalent. So the type of bonding that is exhibited by all these is covalent, and still all of them, they have the structure called simple molecular. So all of them exhibit simple molecular structures. Simple molecular structures. All of them exhibit simple molecular structures. So type of bonding, covalent. Structure, simple molecular. And after knowing the structure, it can give us a clue to the physical state and their color at room temperature. Now, fluorine is a pale yellow gas. Fluorine is a pale yellow gas. Chlorine is greenish yellow gas. Chlorine is greenish yellow gas. Okay, but bromine at room temperature is a red liquid, while iodine at room temperature can be seen as gray, also can be seen as black, but solid. We shall need to account for this. We shall need to account for this. We shall need to account for a case why fluorine and chlorine are gases at room temperature, whereas bromine is a liquid, while iodine is a solid at room temperature. We need to account for this reason, right? It can be examined. They can ask you to explain why fluorine, okay? I can say describe why fluorine, they are diatomic, why fluorine and chlorine are gases while bromine and iodine are liquids and solids respectively at room temperature. What brings about that? Now, for us to come to that, we really need to know, yeah, we really need to know how the atomic radius varies. Of course, we shall look at it independently as we need to really look at how the atomic numbers do. How the atomic number, rather how the atomic radius vary. Then there we shall talk about the sizes and we look at the strength. Okay, we can see the strength of the forces. Or let's see how we can phrase it. Let's see how we can. Let's see how we can phrase it. Okay, let's see how to phrase it. Now, you realize that from fluorine to iodine, the atomic radius, of course, increases since it is down the group of the periodic table, group 7. So the atomic radius increases. So we can say that from fluorine to iodine, from fluorine to iodine, atomic radius increases. When the atomic radius increases, it means that the molecular size and the molecular mass also increases. So molecular size and the molecular mass increases. When that one happens, it means that the magnitude of the van der Waals forces. Why do we talk about van der Waals forces? Because we are saying that the structures are simple molecular, therefore they can't be held by bigger or by stronger force of attraction. So we shall say, and the molecular mass increases. This increases the magnitude of van der Waals. Hence the magnitude of van der Waals forces of attraction holding the molecules increases in the order. The van der Waals forces will increase in the order fluorine less than chlorine, less than bromine, less than iodine, meaning that the forces in iodine are stronger than bromine, stronger than chlorine, which are also stronger than fluorine. That's what it means. Now, the van der Waals forces, the van der Waals forces in bromine, you write words for your case, in bromine and iodine are strong enough, to hold the molecules closer together, to hold the molecules closer together, all right? Holding the molecules closer together or closer to each other, thus existing as liquid and solid respectively. I'm going to give you a further clue on this. But fluorine, you have to go ahead and tell me, but fluorine, however, or you can say however, since you learned English very well, however, fluorine and chlorine, they have their molecules held together by weaker van der Waals forces of attraction, have weaker van der Waals forces because of the small size, due to small size and the low molecular masses. And the low molecular masses. Therefore, their molecules form far apart, or therefore their molecules are far apart. Because remember, we are talking about the states of matter: solids, liquids, and maybe gases. But you know that in gases, in liquids, you have some kind of closeness. However, in solids, but what is causing all this? What is causing all this is the forces of attraction holding these particles or holding these molecules. So this is, we've said that a solid is iodine, a liquid is bromine, while fluorine and chlorine are gases. Okay, because we know that in gases, the molecules or the particles be far apart, and for solids, for liquids, sorry, they be somehow spaced, while for solids they are closely held together. So what brings iodine get to be a solid is because of its high molecular mass, right, and molecular size, which increases the forces of attraction holding the particles together, which force of attraction we've called the van der Waals forces of attraction. But for bromine, because of its moderate, or what I can say, somehow higher molecular mass, so the forces of attraction are not as strong as the ones in iodine. That's why this one forms a liquid. But for these ones, for fluorine and chlorine, the molecules are highly spaced or are highly far apart from each other, simply because of the low molecular mass and the small size. And therefore, the forces of attraction holding these particles are not as strong as the ones in bromine and in iodine. That is what we can explain, or that is how you can put it. If I'm clear to you, type yes, and then I go straight to the variation in atomic and physical properties of these elements. Okay. All right. So now, members, looking at all this, let's go straight to the variation. I told you that before the work I want to cover is not covered today. No releasing you, you leave me here. Variation in atomic and physical properties of group 7 elements. And we shall begin with boiling points and melting points. We shall begin with melting points, or what we call boiling points of these elements. Surprisingly, in 2015, the question came as number 5, paper 2. It was group 7 elements, and the whole logic was about atomic radius and boiling points. Those are the properties that were examined, while yeah, basically I think others will come later on. So for this case, They can give you element. Basically, we shall be explaining the trend. We shall be explaining the trends in these physical properties. So you have element, you have boiling point in degrees Celsius, of course, being the temperature. Then we have melting point in degrees Celsius being temperature. So looking at this, the elements, we have fluorine, we have chlorine, we have bromine, we have iodine. So melting boiling points first, negative 187.9, chlorine, negative 34.0, bromine, 58.2, while iodine, a positive 84.7. For this, we have negative 219.6, negative 102.4, negative 7.2, 113.6. So that is what we are having. And they can tell you to explain the trend of melting points of these elements. They can tell you to explain the trend of melting points. The trend of melting points. Now, if you have to explain the trend of melting points of these halogens, you need to first state it. Of course, we can first state it, of course, the trend in melting and boiling points. You can see generally that it increases. We have highly negative, it ends up positive. Highly negative, positive, implying that generally the boiling point, or depending on what they can examine, melting point. In an exam, if they have talked about boiling point only, don't bring melting point. So increases are from, of course, from fluorine to iodine. Tell me why? Why? Simply because, of course, from fluorine to iodine, the atomic number increases. When the atomic number increases, the molecular size and the molecular mass also increases, increasing the magnitude of the van der Waals forces of attraction holding the molecules. All right? And thus the energy required to break these forces increases from fluorine to iodine. So what you need to tell me, that because we've said that atomic radius, right, increases. Atomic radius increases. When atomic radius increases, molecular mass and molecular, I was supposed to begin with molecular size, then increasing molecular mass. Okay, molecular mass and molecular size increases, thus increasing the magnitude of van der Waals forces of attraction, which force of attraction holding the molecules, holding the molecules, hence thus increasing the magnitude of the van der Waals force of attraction holding the molecules. In which order? In the order fluorine, then to chlorine, then to bromine, and finally to iodine. Thus energy required to break these forces, to break the forces increase, all right, from fluorine to iodine. That is the first physical property. We talk about the increase in atomic radius, that is a marking point. Talk about the molecular mass and molecular size increasing. We talk about the increase in the magnitude of the van der Waals force of attraction holding the molecules. The order, because we see since the atomic radius increases down, then meaning also the increase in van der Waals force of attraction will be increasing down, thus increasing the energy required to break the forces from fluorine to iodine. If understood, type yes, I take you to atomic radius. If understood, type yes, I take you to atomic radius. If understood, all right, all right, all right. All right, so now after having known this, then we can now smoothly move to atomic radius and ionic radius. We are going to talk about those two. We are going to combine them and we talk about them together. The reason as to why I'm summarizing is because this work, we've looked at it before when we were starting the inorganic chemistry. We discussed all those trends. We discussed all those trends. So allow me to take you to atomic and ionic radius too. Atomic and ionic radius. Now, I'm going to give a table of atomic and ionic radii, then we can discuss the trends. We can discuss the trends about this. So we have an element we shall have atomic radius and ionic radius. Fluorine, chlorine, bromine, and then iodine. Atomic radius is measured in nanometers, and this in m's. So this is 0.072, 0.099, 0.114, 0.133, 0.136, 0.181, 0.195, 0.216. So for this matter, I can say state and explain the trend in atomic radius of the elements. Trend in atomic radius of the elements. Atomic radius of the elements. Of course, you've already seen that atomic radius increases from fluorine to iodine, but I want to see what causes all that. Meaning we are reflecting in the periodic properties that we looked at in our first episode of discussion. So If we are to state, let's begin with atomic radius, the trend of atomic radius. The trend generally, if they say state, first tell me that atomic radius increases from fluorine to iodine. Then now I need reasons, because this is a half a mark. You've stated a trend. Explain the trend now. We want to know what causes an increase in atomic radius. So your marking points should involve nuclear charge, screening effect, and effective nuclear charge. All right. So we shall say that this is because from fluorine to iodine, the nuclear charge increases. And what causes the increase in nuclear charge? Because a proton is added into the nucleus, a proton is added to the nucleus from one element to the other. From one element to another. From one element to another. Now, as the nuclear charge increases, also the screening effect increases. So screening effect also increases. Now, a student should be able to know the definitions of the terms I have talked about. Nuclear charge. We are looking at the total number of positive charges in the nucleus of an atom, or the total number of protons. Since a proton is being added, then the total number of positive charges increase because protons are positively charged. When I talk about screening effect is the repulsion of the outermost electrons by those in the innermost sub-energy levels from nuclear attraction. So as a proton is being added to the nucleus, also there is that repulsion, the screening effect, what we call the shielding effect. Okay, the shielding effect, the repulsion of the outermost electrons by those which are already inside from nuclear attraction. However, we shall also find out that much as the screening effect increases, what causes an increase in screening effect? Screening effect also increases because an extra energy level completely filled with electrons is added. An extra energy level completely filled with electrons, is added. But the increase in screening effect outweighs the increase in nuclear charge. The increase in screening effect, outweighs the increase in screening effect, outweighs increase in nuclear charge, outweighs increase in nuclear charge. If the increase in screening effect outweighs the increase in nuclear charge, means that the effective nuclear charge has decreased. So you come and tell me that the effective nuclear charge increases. No. Effective nuclear charge decreases. If the nuclear charge decreases, it means that now electrons are poorly attracted. Even by mere saying that shielding effect outweighs, it means that electrons are more than repelled. They are more repelled than being attracted. So the nuclear attraction, the attraction of the electrons to the nucleus decreases. So effective nuclear charge decreases, all right? Decreases, and the outermost electrons are far. They are far because they are repelled, they are far and weakly attracted by the nucleus. Weakly attracted by the nucleus, increasing the atomic radius. The challenge we find while marking this section is that students don't know when to use these terms. And the moment you don't know when to use these terms, we also may forget to know when to give you a right mark and we cancel things. You need to be strategic. As I've told you, first give me the trend, then what causes that trend. From fluorine to iodine, nuclear charge increases. Why? You're adding a proton. But screening effect also increases. Why? You're adding an extra shell full of electrons. But increase in shielding effect outweighs the increase in nuclear charge. Thus, the effective nuclear charge decreases, electrons are far away and weakly attracted by the nucleus. If clearly understood, type yes, so that I go to ionic radii. If clearly understood, type yes, so that I go to ionic radii. Yeah. So from this one, now you can look at the values of the ionic radii, because I'm going to derive a question here. And the question can be, explain why the ionic radius is larger than the atomic radius for the corresponding atoms. You see, the ionic radius of fluorine is greater than its atomic radius. The ionic radius of chlorine is greater than the atomic radius. The ionic radius of bromine is greater than its atomic radius. The ionic radius of iodine is greater than the atomic radius of iodine. Why? Let's see what causes that. The question would be, describe why the ionic radius is larger than atomic radius of corresponding neutral atom for each element. Why? What really causes this? Why? That is what we really want to, this is what we really want to understand. All right. All right, let's see why. Okay. Now, mm, 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 mm. So, for this particular case, you need first to know the type of ions that we form. Of course, being halogens, fluorine, chlorine, iodine, bromine, all those form negatively charged ions. And to form a negatively charged ion, they are formed by gaining electrons, okay? They are formed by gaining electrons. So the first statement that you need to first tell me is that those ions are formed by, they are formed by gaining, of electrons. That is the mark you would first get, because this one would first tell me that this student knows that these ions formed are negatively charged, but we form negatively charged ions by gaining of electrons. Now, after having known this, then so what? So what? It means that the number of electrons now become greater than the number of existing protons. That is your second statement. You would tell me that the number, after gaining electrons, the number of electrons, okay, let me say that when electrons are gained, after gaining electrons, comma, the number of electrons becomes greater than the number of existing protons. That is another mark. Comes greater than the number of existing protons. So what? It means that since protons have reduced, there is a decrease in effective nuclear charge, because the nuclear charge is the total number of positive charges or protons. So reducing protons, we reduce nuclear charge, which will also now in turn increase screening effect. So we shall say screening effect increases, and a screening effect increases the effective nuclear charge. The effective nuclear charge reduces. Effective nuclear charge reduces. When the effective nuclear charge reduces, it means that the electrons become more strongly repelled, because the screening effect, the repulsion is high. And even the nuclear charge, the force that would have attracted them, they are not well attracted to the nucleus, meaning that the electrons become more strongly repelled by the nucleus than they are attracted. Meaning that in the neutral atom, the screening effect is counterbalanced by the nuclear charge. But still, a student who ends here would be enough. They have told me that the electrons become more strongly repelled by the nucleus than they are attracted, and therefore in the neutral atom, the screening effect is counterbalanced by nuclear charge. By nuclear charge. As simple as that. As simple as that. As simple as that. If you are with me, type yes. Actually, in the next 30 minutes, I'll be through with what I want to cover about the properties. If you're with me, type yes. Okay. Now, let's go to electron affinity. Electron affinity. These are the terms that now we should be remembering. They are the terms that we should be remembering from our previous discussions. Electron affinity. Electron affinity. We shall have element. We shall have atomic number. And we shall have first electron affinity. Let me say EA, kilojoules per mole. Fluorine, atomic number 9, value -354. Chlorine, 17, -370. Bromine, 35, -348. Finally, iodine, 53, -320. All of them are negative. I want to bring in the graphical concept. I want now to bring in the graphical concept. So now these are electron affinities. You need to know before you go anywhere further, you need to know the definition of what first electron affinity is. Okay, you need to know what first electron affinity is. If you are to remember very well the definition, I'm going to consider, let me call it a background. I've not yet set a question that belongs to this table, just background to remind you. When we say first electron affinity, look at this equation. Now you have a gaseous atom X plus an electron to give you a uninegatively charged gaseous ion X minus. Here now, we can define our first electron affinity as the energy given out when 1 mole of electrons combines with 1 mole of gaseous atom to form 1 mole of uninegatively charged gaseous ion. All right? Energy given out when 1 mole of electrons react with 1 mole of gaseous atoms to form 1 mole of uninegatively charged gaseous ions. This is an atom. This is an electron. This is an ion, but negatively charged ion. So energy given out when 1 mole of an electron combines with 1 mole of a gaseous atom to form 1 mole of uninegatively charged gaseous ion. That is it. Or One can describe it as the energy given out when an electron is added to a gaseous atom to form a negatively charged gaseous ion. Still, you are fine. So now the question comes, plot. The question comes, plot a graph. Let me call it my part A, plot a graph of electron affinity against atomic number of elements, B Roman 1. Explain the general trend. Explain the general trend. Explain the general trend in variation of fast ionization energy. In variation of fast electron affinity, not ionization energy, fast electronic affinity. Then another part would be explain why, fluorine has an abnormal value, Now, ladies and gentlemen listening to me, this can be the easiest question for someone to do, because we are applying what we already looked at before. We are applying what we already looked at before. So now, looking at all this, right? Looking at all this, if you had to plot this graph, you realize that electron affinity values, all of them are negative. So since all of them are negative, there is no need of me showing these negative signs. They may be eliminated, or you can put them, depending on how easy you need to plot. But all of them being negative, I may not need to show them. So what does it mean? One can follow up this sketch. And you plot. First, give your graph a title. A graph of fast electron affinity against atomic number. Then you use your appropriate scale. So here you can use the 0, 10, 20, 30, 40, 50, 60. This atomic number. Then here I'm starting from, I can start from like I can start from like 290, or you can start from any value you want. One can even start from 300, say 310, 320, 330, 340, 350, 360, 370. Then you put first electron affinity in kilojoules per mole. You can label your axis horizontally. You can label it vertically or horizontally. So say first electron affinity in kilojoules per mole. You're going to find that your sketch will be like this. Then it goes. I'm assuming it may take that form. It may take that form. So here comes a question now. When they want, I told you that you can discard the signs, negative signs, the fact that all of them have negatives, all right? The fact that all of them have negatives, you can neglect the signs, okay? So when you're explaining the trend, because another person explained the general trend in variation of first electron affinity, the general trend, meaning that there is a general trend. So say generally, first electron affinity, generally, the first electron affinity decreases. Leave alone this simple increase. Just say generally, first electron affinity increases. No. D decreases from fluorine to iodine. Okay. Why? Electron affinity, energy given out when one electron combines with the gaseous atom. When 1 mole of an electron combines with 1 mole of a gaseous atom. So what does it imply still? We shall say, because from fluorine to iodine, I'm going to be using symbols. Nuclear charge increases. Nuclear charge increases. Also, screening effect increases. Screening effect increases. Why? Because an extra energy level, filled with the electrons is added from element to element. But we've said that an increase in screening effect outweighs increase in nuclear charge. Increase in screening effect outweighs increase in nuclear charge. When the increase in screening effect outweighs increase in nuclear charge, what does it insinuate? It means that the effective nuclear charge decreases. Effective nuclear charge decreases. It's as if we are describing for atomic radius. They are related somehow. Effective nuclear charge decreases. When the effective nuclear charge decreases, then it means that the atomic radius increases. Effective nuclear charge decreases, then atomic radius increases, and when the atomic radius increases, it means that the incoming electron and incoming electron, the incoming electron is far and okay, weakly attracted, is far and weakly attracted to the nucleus, giving off low amount of energy. That is it. Giving off low amount of energy. If I am clear, type yes. If I am clear to you, type yes. If I'm clear with those statements, please type yes. We are summarizing the physical properties. We are summarizing the physical properties. We are summarizing the physical properties. So the final part is explain why fluorine has an abnormal value. Why fluorine has the abnormal value. Why does fluorine have the abnormal value? The abnormal value of fluorine is attributed to the following. The abnormal value of fluorine is attributed to the following. Fluorine has the smallest atomic radius. It has the smallest atomic radius, comma, highest electron density, highest electron density, comma, then means that it strongly repels the incoming electron. Strongly repels the incoming electron, and energy is consumed. Energy is consumed to add. Energy is consumed to add the electron to its atom. The electron to its atom. That is it. Energy is consumed to add an electron to its atom. So these are some of the tips that you should really understand from today and onwards. We are left with the two things to talk about. We are going to talk about electronegativity and bond dissociation energy in summary, and we call it a day. All right. Okay, electronegativity. When we say electronegativity, that is the tendency. You need to know it as the tendency, right, of an atom. Tendency of an atom in a molecule to attract bonding electrons towards itself. Tendency of an atom in a molecule to attract bonding electrons towards itself. All right? Tendency of an atom in a molecule to attract bonding electrons towards itself. So still, I'm going to give you element with electronegativity value, and then we describe that trend. The value of electronegativity. For fluorine, it has got 4.10. For chlorine, it has got 2.83. For bromine, it has got 2.74. And then finally for iodine, it has got 2.21. So we can be told to state and explain the trend in electronegativity values of these elements. State and explain, or state and describe the trend in electronegativity values of these elements. All right, so let's see how. Let's see how. When you look at those values, when you look at these values, you can see that the electronegativity value generally decreases from fluorine to iodine. So the stating part, you will say electronegativity decreases from fluorine to iodine. Why? Why? You bring in the all effects that we were saying. Now, if the tendency to attract bonding electrons, we want to see electrons nearer to the nucleus to be attracted to the nucleus of an atom, or they are far away. So you need to know that from fluorine to iodine, I can describe this and maybe you phrase it. From fluorine to iodine, the nuclear charge increases, screening effect also increases because an extra energy level completely filled with electrons is added from one element to another. The increase in screening effect outweighs the increase in nuclear charge. Therefore, the effective nuclear charge decreases, atomic radius increases, and the bonding electrons experience a greater repulsion than nuclear attraction. As simple as that. As simple as that. Electron negativity decreases from fluorine to iodine. I may not need to put the word generally because that is a general trend. That's a general trend. The other side I used it generally because there were some values which are higher than the others, but there is a general decrease in this. So when I say electronegativity, when I say state and explain the trend, so I can simply say electronegativity decreases from fluorine to iodine, which is true. Which is true. So generally may not be necessary, but if put on, no one will take you away from a paper, or nobody will take your paper away, or nobody will mark it wrong. but simply know that the way we're describing other factors of electron affinity is the same way you're going to bring in this. From fluorine to iodine, the nuclear charge increases. All right. Also, screening effect increases because an extra energy level computer filled with electrons is being added from one element to the other. The increase in screening effect outweighs increase in nuclear charge. Thus, the effective nuclear charge decreases. When the effective nuclear charge decreases, the atomic radius increases, and the bonding electrons experience a greater repulsion than nuclear attraction. As simple as that. Members, if you're with me there, type yes, and we look at the final item of bond dissociation energy. Type yes, and I go to bond dissociation energy. Practice makes perfect in this. Good. All right, so let's go to bond dissociation energy. Bond dissociation energy. Bond dissociation energy. I'm going to still give values. And bond dissociation energy values in kilojoules per mole. Part of thermochemistry, bit of thermochemistry here. Fluorine has bond dissociation energy of 158.1. Chlorine, bond dissociation energy of 242 molecules. They're being given molecules, 242.2. Bromine, bond dissociation energy 193. And then iodine, BDE of 151. So before we go deep, I want us to remind ourselves of the definitions of bond dissociation energy and bond energy. Because ideally, if we don't remember those terms very clearly, we may get issues with it. We may get issues with it here. We may get issues with it. So let's remind ourselves. Let's remind ourselves of those terms. Bond dissociation energy, BDE. Bond dissociation energy, BDE. When we talk about these ones, you should be reflecting into your thermochemistry. Right now, we should be borrowing knowledge in thermochemistry work. Wow. Now, when we say bond dissociation energy, we need to really know what it means. When you say bond dissociation energy, we are looking at the heat change that occurs when one mole of a covalent bond is broken. When one mole of a covalent bond is broken down into constituent gaseous atoms. When one mole of a covalent bond is broken down. That is what you need to know. So we say that BDE is the heat change that occurs, when one more of a covalent bond is broken down into its constituent gaseous atoms gaseous atoms. Basically, that is what we call bond dissociation energy. What we are trying to mean, for example, before we go into the details of that, for example, if I have like a molecule X2 gaseous molecule, if it breaks, form 2X gaseous atoms, 2 gaseous atoms of X, we say that the heat required to break that bond is what we call the BDE. So the heat energy required to break this the bond of this covalent bond of this molecule is what we call the bond dissociation energy. All right. So bond dissociation energy is that energy that occurs when one more of a covalent bond is broken down into constituent gaseous atoms. For example, if you have chlorine, like that halogen chlorine, if it breaks down to form 2 chlorine atoms, gaseous atoms. All right. Now, in other words, that is bond dissociation energy. But when we say bond energy, wait to ask. When we say bond energy is the measure of the strength of a bond. Measure of the strength of a bond. So that force, the very force with which the atoms are bonded together, is called the bond energy. The force with which the atoms are bonded together is what we call the bond energy. Meaning, bond energy can be defined as the average amount of energy you've got to break a bond in 1 mole of a substance. There are different factors that affect bond energies. For example, the bond length, the number of bonding electrons, the bond polarity, the delocalization of bonding electrons, depending. So if the bond length or the atomic radius of the bonding atoms or the size of the atoms, if they have large atomic radii, then it means that the bond is long. Longer bonds are weak, and therefore low bond dissociation energy. They require little amount of energy to be broken. If the number of electrons involved in formation of a bond are many, it means that the bond is strong, and therefore it will require much energy. Then polarity or the electronegativity of the values involved. If the atoms involved have got the higher electronegativity difference between the bonding atoms, or if there is a bigger difference in electronegativities, then the bond is more polar and mean that it is more strong, something like that. Then the localization of bonding electrons, etc., etc. But for last year, we are just interested in knowing the difference between BDE and the bond energy. So one can define bond energy as the standard enthalpy change that occurs when 1 mole of a covalent bond is formed from its constituent gaseous atoms. So someone was asking.
Teacher, the definition of bond dissociation energy. is it okay if you say in standard temperature, like in standard conditions?
They have not said standard bond dissociation energy. We just need bond dissociation energy. This is different from when someone says like standard enthalpy of solution, standard enthalpy of sublimation. They are different. This is just bond dissociation energy. You don't need to put in those standard conditions of temperature and pressure. Okay?
Yes, teacher.
Okay, so let's describe now the trend. After having revised it, you see 158, 242, 193, 151. So we want to describe the trend while stating the anomalies in the bond dissociation energy of these halogens. I can record them here so that we can refer to them very well. Fluorine had 158.1. Fluorine had 242.2. Bromine had 193. Iodine had 151. Right. So now, if we had to state the trend and explaining everything here, of course, you see bond dissociation energy decreases from chlorine to iodine. It decreases from chlorine to iodine. But with the fluorine having an abnormally low value of bond dissociation energy, the starting one, it is decreasing from here very well, but initially the fluorine has abnormally low value. That's why we are going to find that fluorine behaves differently from other group 7 elements because of the reasons which we shall look at, because of the reasons that we shall cover very, very, very well. Okay, so now if we are stating the trend, just stating, we shall say that bond dissociation energy, don't be lazy like I am here, write the whole word. Bond dissociation energy decreases from where to where? It decreases from chlorine to iodine, but with fluorine having an abnormally low value of bond dissociation energy. So let's explain these differences and the anomalies. Now, of course, from the reason is this, from chlorine to iodine, we say that atomic radius increases, and when the atomic radius increases, members, the bond length also increases. Atomic radius increases, bond length increases, and when the bond length increases, then the bond strength decreases. Bond length increases, right? Then bond strength, therefore, decreases. When the bond length decreases, it results into weaker attraction, resulting into weaker attraction between the atoms in the molecule. Weak attraction between the atoms in the molecule, requiring a reducing number, right? Requiring a reducing amount, not number, amount of energy to break the increasingly weakening bonds, the increasingly weakening bonds. So if the bonds are increasingly weakening, then they require little amounts of energy, or the small amounts of energy to be broken. But you want to know, why is fluorine having a low bond dissociation energy? Now, fluorine has an abnormally low value of bond dissociation energy because it has the smallest, atomic radius. All right, it has the smallest atomic radius, and the non-bonding electrons, in the molecule, non-bonding electrons in the molecule repel each other strongly. Repel each other strongly. This strong repulsion, does what? Tends to it tends to force the fluorine atoms far apart. The fluorine atoms far apart, thus weakening the fluorine-fluorine bond, requiring low amount of energy to break it. Weakening the fluorine-fluorine bond, thus requiring low amounts of energy to break it. So that is all I had for you today. And in our next lesson, we shall be looking at the methods of preparing these halogens and how these halogens react, the chemical properties, how they react with hydrogen, how they react with the water, how they react with the sodium hydroxide, etc., etc. So in our next lesson, we shall cover the preparation and the chemical properties or the reactions of these halogens. If there is any question, ask so that we see what to do. Could there be any question? If not, I say God bless you and I sign out. Nice time.